Hi, so this video is going to explain PCA, which stands for Principal Component Analysis. So let's start by talking about what is PCA. It's basically a dimensionality reduction technique. Now, what is a dimensionality reduction technique and why do we need something like it? So, dimensionality reduction techniques basically just reduce the dimensions of our data. When talking about dimensions, imagine something like a spreadsheet. Okay, so you have x1 and x2. These are like your two attributes. And you have a and b with some values like this. So each data point here is being described by two values, is being described by two attributes, and thus we say that this is a two-dimensional data. But data in real life is not always as simple as this. One common example to think about a high dimensional data is sensor data. We can have up to thousands of dimensions in our data. So what happens when we have large dimensions of our data or large number of attributes in our data is that, number one, it becomes hard for us to visualize it. Think about the fact that it's easy for us to visualize data that is in two dimensions because we can just plot it on the y-axis and the x-axis. Going to 3D also, it's sort of easy. We can imagine or we can draw 3 axes on our paper and we can visualize it. But going beyond these dimensions, it becomes hard for you to draw all these axes onto like a sheet of paper. So it becomes hard for us to visualize and understand the data. And another concern is that it becomes hard for us to see how all of these attributes, contribute to our output in machine learning. A common issue that arises is called the curse of dimensionality problem. So what happens is that if I have more attributes, I want to capture more patterns. So for me to be able to capture more patterns in my data because of having more attributes, I need more data samples. And the number of data samples required actually grows exponentially based on the number of attributes that I have. And in real life, it's not always possible for us to get this amount of data as our attributes grow. So thus we have dimensionality reductions techniques as a solution such that they can help us reduce the data. And talking about PCA specifically, it does this reduction in such a way that we preserve most of our original information from our data. So what do we mean by preserving information? Try to imagine what exactly dimensionality reduction is doing. Think of the simplest example such that you have 2D data. That means your data is being described by 2 points, x and y. If I reduce its dimension and make it go to 1D, then it's going to have just one piece of information left with it. It's going to have either x or it's going to have either y. So see how we lost data. So we want to do this transformation in such a way that we preserve information. Okay, we're not losing our we're gonna lose information, but we want to preserve that information in some sort of way. So the basic idea behind how PCA does this is that it's going to project each data point onto a new set of vectors. So if you want to think about the simplest example, consider this is this is 1 point. Okay, you can project this point onto this vector, which is basically the x-axis. Okay, or you can project this vector onto the y-axis, okay, which is the blue vector. But how should I choose which one I should project it on? So this basically depends on how spread my data is. Why would we want to project our data onto a direction in which the data spreads the most? Because think about it, over here you only see 1 point, but imagine that you have got many more points. You've got like a bunch of all these points. Okay, if you were to project it onto the x-axis, there's a chance all of these points lie very closely to each other. And thus, if you try to go back from this projected data back into your original data, there's a high chance that you're not going to get the exact same point. Okay, because all these different points ended up all of these distinct different points ended up coming to like a similar set of points. So when you project it, you're not going to get back the same data points. So we lost some sort of information here. But if we had projected onto the y-axis, maybe our points would be a bit further apart. And when I'm going to project it back onto the original data, there's a high chance that I'm going to get the exact same points back. So that means my projection did not change anything. I can go back from A to B and from B to A, and I preserved my information. So this is why I want to go in a direction in which the spread of the data is great. And what is the spread of the data? It's basically the variance. Okay, so we can visualize it. As we can see in this plot over here, most of my data is varying in the x direction. Okay, so it would make sense for me to project my data onto this direction. Maybe over here most of the data is actually varying in the y direction. And here, if we see the data is actually not varying in the x or y, it seems to be, kind of uniform in both of these directions. So high variance is ideal, but as we saw here, that there can be the case when the data is, of uniform variance in both directions. So which one should I go for then? To counter this, we don't just consider variance, we consider something called covariance. Now, covariance basically looks at the relationship between two variables. It tries to see whether increasing one increases the other, does it decrease it, does it have no effect on it? And doing so in this way, we are not just ignoring the other variable completely. We are not just ignoring the other dimension. Like if I were to just, go in the x direction here, I completely got rid of the y coordinate. I completely ignored that other dimension of my data. But here I can consider the direction in which there's a relationship between my variables. So here in this plot, we can see as x increases, y also increases, so this is positive covariance. Here x increases but y decreases, so that's negative covariance. And here increasing x has seems to have no sort of proper effect on y, so we say that there's no covariance. So we try to model the relationship in terms of covariance because it helps capture the relationship between the attributes. So moving on, how actually is the entire process done? It's based on a lot of linear algebra principles, but it all makes sense and it's not very complicated. So there's 5 main steps that we do. First is that we're going to find the mean of each attribute that we have or of each dimension that we had. Then we're going to subtract this mean from each attribute data points, and next we're going to find the covariance matrix so we can capture the relationship between our attributes. And then after this, we're going to find the eigenvalues of our covariance matrix, using which we will find the eigenvectors onto which we will project our data. So what is the fundamental idea behind choosing the eigenvalue and the eigenvector? Like, yes, I want to project my data onto a direction in which it's going to vary the most while preserving most of my information, right? And it could be any vector. Why am I going for something called eigenvector? Why am I introducing this complexity into my problem, So the idea is that eigenvectors are basically vectors on which, imagine that if we apply some sort of transformation, like let's say this is your vector, and you apply the transformation A onto it, this is same as doing scalar multiplication on your vector. So what happens, if you can see here, is that this vector 1, 2 basically became 2, 4, which is nothing but 2 times the vector 1, 2. It became 2 and 4. So what happened is that I just stretched my original vector. I stretched it. I did not change the direction of my vector. I was just stretching it. And why is this fundamental idea of stretching relevant here? Is because like I said, we want the direction, where the data is spread. So if you find an eigenvector that has a very big stretch, that means the data can vary a lot on that vector and hence in that direction. So that's why we tend to go and project our data onto eigenvectors of the largest eigenvalues, because those vectors are actually the ones that stretch the most, in which data can vary the most, and that's the direction in which we want to project our data. So let's look at a very toy example. Imagine you've got like two attributes. So this is a 2D data. We're going to find the mean of this. So the mean of this, for example, would just be 2 plus 4 plus 6 divided by 3. Okay, and you could do the same for physics. So what we do after that is we take our data points and we will subtract the mean of math from each one of the data points here. Okay, because these all are for math. These data points or data values are all for math. And this is for physics. So here you're going to subtract the mean that you calculated for physics over here. And this will become our matrix, centered matrix, usually we call it X. Next, we have to find our covariance matrix. So the covariance matrix takes this shape that we find the covariance between each attribute and itself, and each attribute and the other attribute. Okay, so we've got math and physics, and we've got physics and math, which actually you will realize that they will be the same thing. Because if you look at the formula of how we calculate the covariance, you're just multiplying here. Let's say this is math and this is physics. You multiply them and then you sum them up. And in the next time, this could become math and this could become physics. So it's going to be the same because you're just literally taking a product of two numbers and then you're summing them up. So that's why the covariance between them ends up being the same. I can show you another example of how it's done. For example, if we were taking between math and physics, it would be 2 minus mu m by 3 minus mu p plus 4 minus mu m by 7 minus mu p plus 6 minus mu m by 9 minus mu p. Okay, and then we just divided by 3 minus 1 because we had 3 data points over there. Very simplistic example, but this is how you would find the covariance for math and physics or physics and math. And here, if you were to do it for math and math, it would just be math with respect to itself. So it's mu math by 2 minus mu m plus 4 minus mu m by 4 minus mu m, and so on. So now that we have our covariance matrix, the next step is to find the eigenvalues of this covariance matrix. How do we find the eigenvalues? We find it by setting the determinant of this matrix to 0. Now, you might end up getting many eigenvalues depending on the problem that you're trying to solve. But here, since we said that we're just going from 2D to 1D, so you can just choose one biggest eigenvalue, okay? And after that, we're basically going to find the eigenvector that is corresponding to this eigenvalue. And how do we do that? As I explained before, the fundamental idea is that applying some sort of transformation onto that vector is same as a scalar multiplication with that vector. So think about it. We literally reduce a matrix computation down to scalar multiplication, which is very computationally efficient. So that's another reason why the whole idea about eigenvectors exist. So anyway, we solve this equation and we find our eigenvector, and then I just take my centered data x here and I multiply this by the eigenvector to give me a vector on which my data has been projected onto. Okay, and we tend to call these vectors now principal components. And since I had only projected it onto one dimension or one direction or one vector, it's going to be just one principal component, and we call it principal component 1. So there's a chance that you may decide to project a 1000 dimension data down to 50 dimensions, then you would have like 50 principal components and so on. And each one of these principal components is actually explaining a different percentage of variance in your data depending on the eigenvalue, right? Because eigenvalue was what did I say eigenvalue was? It's the stretch, right? So it's going to explain the variance hence. So we can calculate the variance that is explained by this principal component by basically taking the eigenvalue of, let's say, principal component 1, if we were calculating it for that component, and then summing it by all of the eigenvalues. Okay, so the next idea is that the more principal components we choose, the more information can be preserved. Why? Because think of it, we've got more more attributes that are, representing your data point. So more principal components can lead to more information being preserved, but how do we choose on the right number of principal components? So what we can do is that we can plot the cumulative cumulative explained variance graph. So what this will tell you is that, let's see, first of all, how to find this cumulative variance. When you have you can calculate for principal component 1 using this formula, the explained variance, and we can plot this as 0.25. To get the cumulative explained variance for the next principal component, we just add 0.25 plus 0.2, which is the explained variance for PC2. Okay, and this is going to give you a value of 0.45. For principal component 3, we can add the explained variance of the third principal component, which is 0.18, and this is going to give you a value around 0.63. So we can do this for all our principal components, and what we can infer here is that, let's say you wanted to explain 70% of the variance in your data after you do the dimensionality reduction. So we can see that if we go to the graph and look around the 70% explained variance, this corresponds to somewhere like 10 principal components. So by plotting this cumulative explained variance graph, we can infer how many principal components, we can get an approximate value of how many principal components I should keep in order to explain this much variance. Okay, we can choose, I want to explain 70% variance, or I want to keep 95% of the variance, depending on what's the percentage that you want to capture. Okay, so the last idea is that when we say we're going to project our data onto a set of vectors, and we can choose a bunch of principal components according to the amount of variance that we want to explain. But remember that the number of vectors that you can project onto is limited by the rank of the covariance matrix. So what is rank? Simply, it's the number of independent rows or independent columns that we have in a matrix. So imagine if you have like a 3x3 matrix, like really just random numbers. So here we see that there are 3 independent rows. So we can say that the rank of our matrix is 3. What this means is that using these 3 independent vectors, I can go anywhere in the 3-dimensional space. So these vectors actually span this 3D space, okay? That means they vary in this 3-dimensional space. So, and in PCA, we want to project in the dimensions in which the data is actually varying, right? So this is why the rank of the matrix is so important. It's a bit clearer to think of it in a bigger dimension. Like, let's say if you had like 1,000 attributes, but you only had like 50 data points. That means the number of dimensions that you can actually project onto, or the number of principal components that you can have, is actually less than or equal to 50. Because even though your data is like having 1,000 attributes, it's actually living in a 50-dimensional subspace within, the bigger 1,000-dimensional space. It's, again, easy to think of something like if you have a vector which is maybe in 4D, so we have 5, 4, 3, and 0. So it has, all the values for like the first 3 dimensions, but the last dimension is actually 0. So even though it's a 4D, vector, it's actually living within a 3D subspace. So we cannot project our data into more dimensions than where it actually lives. So this is the key point, that you cannot project your data onto more dimensions than where it lives, which is basically defined by the rank of your covariance matrix. So this is all about PCA, and I hope that you found the information useful. And if you've got any questions or suggestions, you can leave them out in the comments. Thank you, and until next time.